Hey, hi everyone. Today's Leetcode question is maximum candles allocated to catching. Let's reset this. Or let me time this out. Let me check how much time will it take. Sensing that this is a medium question, I'm expecting a 40 minutes. Let me check how much time will I take to solve this question or whether I would be solving this question or not. Oh, 40 minutes is my break. And even if I can't solve it after 40 minutes, I'll just go to the editorial and learn something. Either I will win or I will learn. So I won't get upset. Okay, let's start. The great energy. And you're given a zero indexed integer array, Candice. So an array named Candice is there. Okay. Each element in the array denotes a pile of candies of size candies of I. Okay. Each element denotes a pile of candies whose size is represented by the number given at specific index of candies. You can divide each pile into any number of subpiles, but you cannot merge two piles together. Meaning, a pile can be divided into multiple parts, but you can't merge two piles. I mean, two piles of represented by two different indexes of an array into one. So that's it. And you're also given an integer k. You should allocate piles of candies to k children such that each child gets the same number of candies. Each child can be allocated candies from only one pile of candies, and some piles of candies may go unused. Return the maximum number of candies each child can get. See, the rules are you should allocate piles of candies to k children. Okay. And each child can be allocated candies from only one pile. It means one pile can be used for two children, but one child shouldn't get candies from two piles. Okay, it's a many to one relationship. As piles to children, piles is many. No, piles is one. Children can be many. One pile to many children, but one child only one pile. Okay. Return maximum number of candies each child can get. Okay. Then also you don't need to use a pile if you don't need. Okay. Since this is three. Okay. Number of children are three, and let's look at the candies. What is this? 586. First pile contains 5, next pile contains 8, and the next pile contains 6. Explanation. We can divide candies into two piles of size 5 and 3. Candies of 1 has two piles, and candies of 2 into two piles of size 5 and 1. We now have 5 piles of candies of sizes 5, 5, 3, 5, and 1. We can allocate the 3 piles of size 5 to 3 children, and it can be proven that each child cannot receive more than 5 candies. Okay, that's a good one. Let's go to next example. Okay, the candies are 2, 5, and K is 11. Okay, one pile contains 2, and another pile contains 5. Considering that at least each child should get one candy, there should be more than 11 or at least equals to 11 candies in order to distribute. But if you count the total sum of candies here, it is 7, which is less than 11. So here is our good edge case. If let's sum of the candies in the array. I mean, let's remove this if for a second. That might be our first edge case. Int sum equals 0 for a second for int I equals 0 int I in candies sum plus equals to I. So now if sum equals to 0, Wait. If the sum is less than k, that means that the amount of candies available are insufficient. So it's a non-negotiable thing. We just return 0. That's it. Now, what's the next case? Let's look here. It's 5, 8, 6. What's the minimum number of element in the array? It's 5. Now, if we can divide it, 5 minus 8 is 3, and 5 minus 6 is 1. So, after subtracting each element, we can find that the minimum element of the array will be the maximum compared to everything. So, then we return it. So, we take another condition. Else, in the else statement, we're going to write the code that we check for the minimum element in the array and what it is. Is the given array sorted? No, it's not. Okay, what can we do? We'll just take arrays dot sort candies. I hope this would work. So we're gonna take first element. What would be the first element here? 5. The minimum element should be taken first, right? So for generally it can be the answer only if it's the maximum element after subtracting. Then we can do one thing. Hmm, let's do one thing. Uh, let's take a rough notepad. Can I get a notepad? I'll just show this here. Okay. Consider a candy array 5 comma 10 comma 6. 5 comma 1 comma 6. Now, according to our minimum element, what we'll get? First one will be 5. Okay. Next one will be 5 comma 7. And the next one would be 5 comma 1. So, would this solve our problem? So, if 5 are taken to each student, we're left with 8. One pile can get many. Like 5 plus 8 is how much? 13 plus 6, 19. 19 can't be divided among 3. Okay, next. What about 5, 12, 6, 18 plus 5, 23? What if we take it as 5, 7, 12, which is a multiple of 3? 5, 7, 12 will be 24. 24 chocolates. A, a child, we're given a rule, right? We should allocate piles of candies to k children such that each child gets the same number of candies and each child can be allocated candies from only one pile. Okay, one pile can contribute candies to two child, but a child should get candies from only one pile. Okay, so what is the max number of candies a child can get? It's obviously uh, the pile number, right? Pile number, pile count. Okay, it would be somewhat good. Pile count. So if this is the case, you can take it either as 5, either as 12, either as 7. Now, if you take the full pile, let's look it here. 5, and this one is 12, and this one is 7. 5, 12, 7. The differences would be 5, and 5, 7, and 5, 1. I mean, 5, 2 here. And considering the equal distribution, 5, 5, 5, remaining would be left. We can't give each children more than 5 because this is the minimum limit that is imposed on us. Consider that we don't want to use this, then we are going to distribute the pile among these two. Okay, so a child, the rule is each child can be allocated candies from only one pile. So At max, we can give from this pile, that is 7. If pile 5, if we eliminate pile 5, we have total 19 candies, which if we share among 3 students, it would be 6, right? 6 for each. Like pile 2, 6, pile pile 1, okay. You can take from the 12, child A gets 6 from pile 1, and I mean pile 12, and child B gets 6 from pile 12, and child C get 6 from pile 7. Okay, this makes some point. Okay, the maximum candies the child can get would be 6. Right. So what's the case? First thing, we'll check if the given candy sum is greater than more child. This is the edge case which is satisfied. Now we figure out the minimum element and we figure out the last sum. We already calculated the sum, right? Figure out the minimum element first. And if we see in this array 586, in 586, what happens is the maximum number of chocolates, if the array is sorted, it would look 5, 6, and 8. And if considering the first minimum element, which is 5, and considering this can be a maximum a child can get if they want to do it equally, uh, let's do one thing. Let's look into the sum. What is the sum? Sum is 5 plus 6, 13. No, sorry, 5 plus 6 is 11 plus 5. 8 is 19. Sum is 19. Which when divided by 3, how much is left? The thing that is left is it's 1, and we'll get 3 6 are 18, and we're left with 1 chocolate. But the thing is, 5 is the bare minimum that we can get. So here lies the question. So if we're given an array 586 and the k, we'll first make a sum divided by k, and if the quotient obtained is available in the minimum pile, that's it. We're done. We can just result it out. But if we check a case 5, 12, 7, okay, when sorted in the order, it will be 5, 7, and 12. And what would be the sum? The sum would be 5 plus 7 is 12, 12 plus 12 is 24, and 24 divided by 3, it's actually 8, buddy. And is there a 8 here? No. What's the minimum element? 5 can be given. What's the next minimum element? 7. Since can 7 be given? No, not actually. If all 7 are given, okay, if 5, 12, 7 are given, like a child can't get from 2 piles, right? But a pile can contribute to 2 childs. So how much is minimum available? 5. So if a child gets 5 chocolates from this pile, other child can't get more than 5. I mean, child A gets 5, child B should get, their child B and C should share from these 19 things, which can be, it can't be divided into equal parts actually. The equal parts at minimum they can divide is 5, 5. If in case we just unuse this 5, we have 19 here, and 19, can it be divided among 3? We are given the rule that each child can be allocated candies from only one pile. So a child can get candies only from one pile. So one pile can contribute to 2 childs, but from child side, candies should come only from one pile. So 12, 7, it's 19. It can be shared among 3, which would the modulo would return 3, 6. So the maximum we can get is 6. Like if 12 7 is taken, 24 divided by 3 is not available. So we omit. Okay, I'm trying to generalize this issue. We can't take 5 12 7, so we just took 12 and 7. The sum would be 19, which by divided by 3 would get 3 6 or 18. So 6 chocolates can be actually shared from both the piles. 6 6 and 6. It's a common thing. LCM of 12 and 7. Nah, it's not LCM and HCF concept. It's just the equal divisor. Okay. So what's the thing that we're going to do? We'll check the minimum element first. I mean, in 5 12 7, what happened? In this case, we can directly return that 5 is the thing. Okay, leave this case. In this case, 5 12 7. The minimum element is present in every array. But when taken over, when we find the differences here, let's look at the differences. After sorting, we get 5 is minimum element. Next, 5 minus 7 would produce 5 and 2. And then 5 minus 12 would produce 5 and 7. So if we sort this stuff again, what we get? We can actually, we have 7 here. So a number is more than 5. And there are two numbers more than 5 where we can actually shift it. I mean, what can we do? Think, think in a logical way. It's 5. If we remove 5, we have some. Okay, we found that 5 exists everywhere. That's not the case. I mean, there is a case where the differences are greater than 7. Difference is greater than min element. So if the difference is greater than min element, what we gonna do? We're gonna subtract sum minus minimum element. What is the minimum element? 5. Now we got 19. So we're gonna divide sum by k. What we have got? We got a number, which is 6 in this case. And can we return it as a maximum? Obviously, yes. So that's the case, it's correct. So what do we need to do? Since we got the minimum element, what we gonna do? Okay. Now the main thing is we need to check if the difference is any difference is greater than array. So for int I is equals to 0, I less than candies dot length I plus plus. We're just gonna check if the if the minimum element double, if any element is greater than or equals to double the minimum element. Okay, let's check this case. We'll check this one. What if 5 12 5 10 and 7, 5 10 and 7, I mean the case where it's exactly equal. We remove 5 here, we get, I mean 5 5 comma 5, we get an 5 comma 2. If we remove 5, what we gonna get? 17. 317. It can't be divided by 3. So we can't share 6 and 6 and 6 because 6 3s are 18. So it obviously will be 5 again. Okay, the rule is pretty simple. For int in I, if uh, we're gonna check only one thing. Mm, we loop over the array, find the maximum element double than the array. Okay, if 2 into, okay, we're gonna write it here, int min is equals to candies of 0. That's the minimum element we have got here. And if uh, candies of I is greater than, in equal to case also it's not working, so it should be only greater than case. If candies of I is greater than 2 into minimum, then it's only then what we're gonna do? We're gonna remove minimum. Sum minus equals to minimum. We'll remove minimum and then return sum by k, because we just need to get the coefficient here. So if that's not the case, what are we gonna return? That's it, guys. I mean, if you figure out any element is greater than, wait. This shouldn't be in a loop. It sucks. If it is in a loop, we get many elements greater than 5. It obviously shits the process. If candies of I is greater than 2 into n, what do we gonna do? After this, we break. That's it. Nothing else. Because we already sorted the array. We'll get the just the next minimum element. We're just going to iterate till we get an element that is double greater than the double of minimum. Okay, return sum by k. Will this work? I think it will work. Just clear this out. Else condition is going good. If both of them are wrong, what are we gonna do? We're gonna return 0. That's it. Let's run this code. I think it will work. Let's check. Else without if. Hey buddy, I actually did an okay. That is not out. Hmm. Sum by k. Lossy conversion from long to int. Okay, let's make this int. Hmm. In okay. Unreachable statement. Oh god, oh god. Okay, get it now. If I break something, I shouldn't use return before. Hmm. I'll just come out of the for loop. Then I'm gonna return this. Will work. Error unreachable return statement. Basically, reward against the no return statement. Oh, it's a 586. Output as 6, but expected as 5. Okay. Next element is 14. 14 by 3. 3, 6, 3 5s are 15. So, why did it give 6? I didn't account for the. Okay. If we figure out any element greater than, then we're gonna do this. Otherwise, what are we gonna do? Sum, which is 5 plus 8, 13 plus 6, 19 by 3, which is automatically 6. That's why it went wrong. Okay. I get it. Hmm. So the for loop hasn't went through any decision. Else, we need to write else if here. Else if now, if the for loop isn't gone, what do we need to return? Command C. We don't need a break here, I guess. Return this and here return minimum. But yeah, worked. Made a wrong turn here. Why? 475. The minimum is 4. Okay, can we share 4? Yes, 4, 4, and 4. 1 plus 4, right? But expected as 3. Why? I didn't get it. See, each child get K is 4 here. Okay, there are four children. 4, and if we remove 4, we have, okay, if the minimum, I get it now, I get it. Use this test case. It is that if, see, we are given 4, 7, 5, and its K value is 4. So we need to check one thing. If K is greater than 4 plus 7 is 11 plus 5 is 16, but we can't exactly give 4 here, right? One was given 4. A file can share, a file can be shared. I mean, a student should be shared from only one file. A file can share multiple students. So it must be at least greater than, it must be double in order to share. But it's not double here. That makes the problem. 475. Okay. Hmm, what can we do? Check. Let's check this out. It's 4 actually. Hmm, okay. Minimum, the maximum we can give is 4. But if we take this, it's 12. 12 can't be divided among 4. We figured out that this is not working. So what are we gonna do? If minimum is candles of 0, int I equals 0, we checked no element is double. Okay, no element is double. Then what do we do? We're gonna, then after this, what we're gonna do is we're going to do one thing. 4 plus 7 is 11 plus 5 is 16. What if we subtract it? I think in a dumb way. 4, 7, 5. 4, 7, 5. Subtract it, I would get 4, 4, comma 3, 4, comma 1. 4, 4, comma 3, 4, comma 1 can't be distributed among 4 people since there are no 4s here. Okay, what the hell can we do with this? If this is 4, and if this is 8, we can do this. But hell no, it's not 8. The elements, all the elements are less than double of this element. In this case, the sum is equal, it's exactly equal. So 4 plus 7 is 11 plus 5 is 16, not 0, it's equal. We can do one thing. Sum is a multiple of 4, but we can't give 4. Hmm. To remove 4, what's the sum? 7 plus 5 is 12. Can 4 do that? Yeah, it can. How do we exactly solve this problem? I'm not getting it. See, 4, 7, 5. If we remove 4, we get 7, 5, which needs to be shared across 4 people again. So doing direct mode won't solve the problem here. What can we do? The total sum is a multiple of 4, but that doesn't make it happen. 4, 4 is 16, but we can't share it like that too. What's actually stopping us? So if we take the difference, we figure out that the number of fours we have should exactly be to the number of students that we're going to give the candidates to. And here the number of fours that we got are just 3 and not 1, not 4. So we just subtracted 1 from each. So this might be a good approach. So what is it? We're just going to subtract the minimum possible number. That will be 0, 3, 5, 0, 3, 1. And 0, 3, 1. Can we? I mean, if we subtract it, we can't replicate since we need to give it to 4 persons. The difference can't be there to where we have given to. So array of 5 and 4 are not equal. Let's check the constraints. How much can the size of array? Can be 10 power 5, it's very lengthy. And the k can be 10 power 12. We can't decide actually. So what are we gonna do? Hmm. We're going to create a difference array. If we take a new approach, I think this approach won't work. Let's take a new approach. Given 4, 7, 5. After sorting this array, we got 4, 5, 7. And then we need the k will be some number. We'll check if min is greater than or equals to k. If it's the case, then we can directly give return k. Now, if minimum is equals to k, then what are we gonna do? Subtract mm, subtract k, subtract min into uh, length of array minus 1 times because those many indices are left. What do we got? We get something now, which is 12 minus 8, which is 4 again, 1 and 3. Can we share it? Okay, 4 is again being a multiple. That won't work. This won't work. Hmm. What if it's 7 and 6? Even then we can't do this shit. Hmm. This is not going to work. Then if a mirror element equals to k, then what are we gonna do? Subtract 4, subtract k from each index. If we get k in any index, then return k, else return k minus 1. Or we can see this. What if we get after subtracting? We get 0, 1, comma 3. So this is the maximum. So we can say we can return max of array. Can we do so? What if we take 4, 7, and 6? What do we get? If we take 4, 7, and 6, it would be 4, 2, and 3, 0, 2, and 3. Even then, we can do nothing about this, which always less than 4, right? So returning max of array is the best approach there. So the minimum element equals to k. We did this. If the minimum element is greater than k, we just return k, which child can get. No, this statement is wrong. We just subtract first. If the minimum element is greater than or equals to k, so that's the case here. Check this case. This one. 586. Minimum element is greater than k. We subtract everywhere. What do we see? We get 2, 5, 3. Then we go for next element. Subtract. What do we see? 4, 1, 4, 2. So what are we going to return? We're gonna return 4 in this case. No, 5. If we subtract this, if we subtract 5 from this, we get 0, 3, 1. So k is less than. If so, what does that mean? We can make a case here. If the minimum element is greater than or equals to k, then we can return minimum element. Okay, we can return k here. If minimum element equals to k, just like this case, we're gonna subtract k from each index. What do we got? That's 0, 3, and 2. And the maximum is 3. So that's it, we return the max. So I think this is going to work. Okay, first we sorted the array, and now if sum less than or equals to k, return 0. Okay, int minimum scan is of 0. If I equals 0, I less than candidates dot length I plus plus. What are we gonna do rather than using a for loop? Okay, what if we used a for loop? We see that no element is greater than double of the size, but we see that whether we can do this, right? We can just subtract. Okay, what are you gonna do? We just subtract. Else, if minimum, okay, if minimum is greater than k, return k. Minimum, no. We can't use this case if it has 6. Can we make this? 687. Consider a case of 687. Can we take 6 there? 6. Yes, we can take a 6. So, okay, done, buddy. This is it. Next. Else. We're going to use the else here. Let's remove this. In this if, what are we going to do? We're going to check. We're going to subtract everything. For in I equals to 0, I less than candies dot length I plus plus. Hmm. No, since the array is sorted, we want to get the maximum element. We don't even need to iterate over a loop, right? See, if minimum is greater than k, then we return. If it is equals to k or less than k, what are we going to do? Else, return the maximum element, which would be candies of, we're gonna do int x is equals to Candies dot mbmgth. Candies dot length x, candies of x minus 1. So what we're gonna return is uh, the last index, which is candies of x minus 1 minus the minimum element. So what happens here? Uh, it won't make a difference, right? Will it? So what would be this? Uh, we'll see this here. What has happened here? 4, 7, 5. After sorting, it will be 4, 5, 7. Subtract each, you get 3. So what do we got? If you want to access the last element, which is candies of x minus 1 minus minimum, think that will work. Oh, wait. This is all right. Let's run this again. Run again. Hey, wait, did I miss anything? Return int k. Just make this int here and run it again. Oh god, what happened here? 5, 8, 6, the minimum element is 5 and k is 3. The output is C. If sum is less than k, return 0, else minimum. If the minimum is greater than k, yeah, it is greater than k. So then what do we going to return? Return int of k. And why isn't it occurred? This case passed and this case isn't. Why so? Let me clear the code for a minute. Else, if sum is less than k, return 0. Int minimum is the candidates of 0. If the minimum is greater than k, yes, it is as given in the test case. The minimum element is 5 here, which is greater than k, from k. Then we're going to return int of k now. Why didn't this test case pass? Confused, very much confused. It only occurs if it is greater than k. And yes, it's greater than k, right? Why it's not understanding this? See, initially the sum is 0. We calculated the sum. We sorted the array, which gives us 5, 6, 8. Now we're just taking first element, which will be 5. If sum is less than k, then we're returning 0. Else we went inside this. We initiated a min with candies of 0. And then we're checking whether min is greater than this. See, instead of return int k, oh, what have I done, buddy? We need to return min, na? Ah, my brain is not working. Again, God, why? 1, 2, 3, 4, 10. What's the minimum element? 1. No, subtract. What's the least possible minimum element? 4. Output is 9, but expected is 3. Okay, this is not going to happen like this. We need a new approach. This approach won't work because you can get many elements which are greater than this. Okay, 1, 2, 3, 4, 10. Mm-hmm. This element equation everything, but that won't make sense. You can give more than one. See what happens. Check the difference. The difference is double. So we just forgot. the doubling condition here, and that made things worse. So if the minimum is greater than k, then we return min. Else, what we gonna do? This is a case when no element greater than double exists. Okay, case where no element greater than min 2 into min exists. Okay, but in this array 1, 2, 3, 4, 10 elements greater than min are available. 1, 2, 3, 4, 10. So what we going to do? 2 into 2 is 4. 3 into 3 is 9. Yes. Sorry, 3 into 2 is 6. 6 is a district. 3 can't be distributed. Yeah. Can 3 be distributed? Yes. No, bro. I'm just giving up. It's 45 minutes already. I'm just looking into the editorial. But I just want to give a little thought whether I can do this. Okay. The candy should be given equally. I think this is some sort of greedy approach. Even though I saw the array, I was unable to do it. So 3, 14 divided by 5. Is it possible? 3 plus 4 plus 10 is 3 plus 4 plus 10 is actually 17, which is 17 mod 5 is 3, and it is 3. Okay, just near, I guess. Why can't I try it again? Okay, I will try till 1 hour. That's the last one I'm going to do. So we check this, it's double exists. Then we update. Okay. 1 into 2, 2 exists. 2 into 3. 2 into 2, 4 exists. 3 into 2, 6. Does it exist? Yes, it does. 4 into 2. Does it exist? No. 6. Element greater than 3 is available. So what are we going to do? So, okay, we're going to take the sum with that element. Okay. We're going to iterate a for loop for int I is equals to 0, I less than x, I plus plus. We're going to check if candies of I is greater than mm, is greater than min, 2 into min. If it is greater than 2 into min, we're going to update min. Min is equals to candies of. So we're going to introduce update min by each index. I mean exactly is the first index previously, but now we're going to iterate it. So we're going to make it by 1. Mhm. We need to update the index by 1 each time. So what are we going to do? We take a value count, int count equals to, this is actually 0 here, candies of count, count plus plus equals to candies of count. No, candies of I, it's double, checking, and figure out something, figure out that, okay, 4 is the last element, can be Just optimize this. The last element is 10. Okay, 10 can't be the double of 10. 4. Can it be the double of 10? Yes. So what we're going to do? We're going to take a reverse shift. Equals to x minus 1, I greater than 0, I minus minus. If candies of I, we're just going to do candies of x minus 2. Candies of I is greater than, no, 2 into candies of I. Yeah, right. 2 into candies of I is greater than, no, it should be less than, right? Is less than candies of x minus 1. It is. So let's look at this. 2 into 4 is 8. So it is possible. So what are we going to do? If this is possible, then basically going to take, we're going to subtract sum minus equals to, we're going to subtract all the elements from this sum. No, I think this is a very lengthy way. Let's solve it to the end. You are given an array, so on, goal is each child gets the same number of candies. Okay, to understand that, for example, suppose candies are 5 to 6 to and k equals to 3. The first, since each child candies must come from single pile, the greatest number of candies each child can get is at most equals to the largest element in the array, in this case 6. If we try to give 6 for example, 7 candies to each child, we would need to combine candies from multiple piles, which is not allowed. So that is not 6 for 6 candies, it is not possible. After determining the upper bound, you can start from 6 and go to till 0 until you find the first number for which the allocation is valid. So what are we gonna do? Instead of taking the minimum, we took the reverse. Okay, think in an opposite way where you got stuck. This is what I learned from this problem. So 6 is not valid. Then we took 5. Then we extended 5. 5 is 1. But again, it's not possible after that. So 3, it's not possible. Then 4, 4, it's not possible. Then 3, 3, 3, 3, it's possible. So it is 3. After determining the upper bound, you can start from 6. Hey buddy, I understood something and I think I can do this. And this case reminds here, we gotta do one thing. Uh, See, we know the max element int upper boundary equals to what it is. Let's take the length. Okay. On it, candies of candies. Take that because I did it. Int x is equals to candies dot element x minus 1. This is the upper limit. Let's check. Does upper limit exist? No, it doesn't exist. In all the arrays. So what are we going to do? For x equals 6, now value contribution exists because number of candies less than 3 into 6 is not possible. Next, 5. 3 into 5, 15. For x equals 5, the first child can get kind of 5, and the second child can get kind of from third 5. Or it is impossible to get 5 candies without combining remaining 5. Similarly, for x equals to 4, matching the 5 to not. So we can give so we can give 3 candies from the first 5, the first child, and 3 candies from the third pile, and the second child. From the third child. 60 is the largest number of candies that satisfy all conditions. It's our final result. Okay, it's just like The first would be the binary search. Okay, so let's first try to answer a slightly different question. Given a target number of candies X per child, can we distribute the candies so that each child will get exactly X? Check this. We calculate how many children each pile can deserve. For example, if candies and X equals to 4, first and the third piles can serve one child each with some left over, while the second and fourth piles can't be used because they contain fewer than X candies. Okay, 5, 6 is 11. So we can actually remove the unworthy things here. That's cool. That's 11. 11 mod 4 is actually not possible. 11 mod 4 is 4, 4, 4 2 are 8. It's 2. 4 3 is 12. So we reduce 1. 11 mod 3 is possible. 2 are 8 is 3. We return small 3 basically. We can do this. So let us take this test case. Remove all the unworthy candidates. Okay, don't think big. Won't work. Generally, each file can serve up to candies by X, children possibly with some leftover candies. By summing the number of children each file can serve, we can easily determine if the allocation is possible by comparing the total number of children we must distribute candies to. Additionally, note that if a validation distribution exists from the given number X, the distribution is also possible for any number smaller than or equals to X. Conversely, if we cannot allocate the candies such that each child receives X candies, then it's impossible to distribute them in a way that gives a child more than X candies. This monotonic property allows us to use binary search approach, where we check if a distribution is possible for middle values of our search range. Okay, we check if a distribution is possible for the middle value of our search range. Based on that, we either move the upper half of the range if a distribution is possible or the lower half. Oh god. So the left is initially 0 and the right is initially 6. Oh my god. Oh my god. This is just actually pro. Pro. This is actually floor or ceiling concept. My dumbass couldn't even think of it. It's just a pattern. We can directly, now I understood it. Buddy, this falls under ceiling pattern of binary search. Questions. Buddy, this is pretty clear. Just need to think that this falls under this pattern. We can sort the array. First thing. And there is obviously a lot of chance that we can think of it. But I haven't since I don't know the pattern, but I got to know it right now. Understood. What is the floor? Element which is greater than or equals to the given element. Yeah. So if k equals to 5, uh, what is the ceiling? Element greater than or equals to, right? So we can take 0 to 6 is our range, and in this range, this is just a variation of this. Is 5. Max element is 0 to 6 our ranges. The middle element would be 3. Candies can be allocated. Yes, buddy. What about 5? Candies cannot be allocated. 3 cannot be allocated. So 5, 4. 3 is the greatest number of candies each child can get. Ah, this is where I lost. Just some common sense. Think, we sorted. Erase, dot, dot, erase dot sort of candies. And next, in low equals to 0, obviously. int I would be candies of length, candies of candies of length. So now, how are we gonna do? I forgot about the edge case for int I in candies. Sum plus equals to I. If sum less than k, return 0 to be order, return 0. Ignore int high while low less than equals to high. Int mid equals to low plus high minus low minus low by 2. Hmm. If mid hmm, can mid be allocated? How are I gonna check whether it can be allocated? Let's see. Check out the mind research explore card. Open this recurring tab. Hmm. This one research and type. But check termination if they can work. Back to job. Okay. So type on like this. We are playing guess game. And yes, we can number from 1 to n. We have to guess the number which I picked. Okay, okay. Let's make this. What is this? Okay, it's just a fact. Leave this. So we have understood that it's a variation of binary search. But now, what I'm going to do implementation. Hmm, copy this code, paste it here. Let's check. Okay, let's check. Do we have any other approach for this? Not actually. We're going to search fast. Start with choosing my left. Hmm. Always put left hand side with adaptation to eligible service already. Okay. Let's say I have I equals 0 and equals m by 2. If I plus t satisfies the condition, then I to I plus t, I substitute d by 2. When d becomes 0, have your answers. What we are doing here is moving as fast as possible to the answer. And let's go with left hand side have just to keep okay. If possible. Mm-hmm. Okay, these questions are on binary search, guys. We just need to make sure that we understand this concept. I'm going to make a video on this, find the search template. because many of the interview problems are being asked on binary search. Just need to know this. Okay, while left is less than equals right in the middle. Okay, this is a common thing we gonna do. Left plus right plus 1 by 2. Oh, so calculate the middle value of the current range. Left plus right plus 1 by 2. Serious? Also, don't get it. I mean, okay. Even from this, then, yeah, here, 3 plus 6 is 9 by 2. Isn't 5. That's 4, dude. 7 by 2 plus 3. How did he get middle as 5? Okay, left plus right plus 1 by 2. So that each middle child gets a middle candies. Can allocate is the function here. If it is, then if left equals to middle, else right is equals to middle minus 1. Return left. This is some cool question I'm unable to answer, but it's just a variation of mind research. And what do you do? Initialize the total number of children that can be served, max number of children. Iterate all over the files to calculate how many children each file can serve. For file index 0, file index is then candies dot length. Number of children plus equals to candies of file index by number of candies. Mhm. This is some pretty badass question. Okay. It's basically a variation of binary search, guys. That's it for this question. We just learned to apply binary search here.